Hello, welcome to lecture 16 in the Aero584 guidance and navigation. And today I will talk about Kalman filters. So in the last lecture, we talked about state estimators and we focused on the predictor type state estimators. In this lecture, we'll talk about the filters and I'll tell you what the difference between predictors and filters is. Uh, the same way we derive the optimal predictor in the last lecture, we'll derive an optimal filter, and the optimal filter is more commonly known as the Kalman filter. Okay, let's start. Um, okay, so like I said, last time we discussed predictors. Okay, let me make sure that this is working. Great. Okay, yep. So last time we derived a predictor, and predictor is a state estimator. And the key property which distinguishes a predictor from a filter is the fact that it predicts X, it predicts the state at step k plus 1 using data only till the kth step. And we saw that the equations of the estimator equations of the estimators were given by these three guys. This is your real system. Oh, whoops. This is the real system, not the real, I wouldn't say the real system, it's just the system to which you apply the input and you collect the outputs, measure the outputs, and these are the estimator equations. So this is the equation that estimates the states, state estimator. And the state estimator has a copy of the dynamics, and it has this output error term, which is injected using this gain kk. Kk, the optimal gain kk is given by this equation, where this matrix pk, which is also called the state error covariance matrix, is propagated using this equation. So in this lecture, we will be focusing on filters. And the key property of a filter is the fact that it is using data up till step k plus 1 to produce an estimate of the state at step k plus 1. So intuitively, predictor predicts into the future, and filter is really like the literal meaning of filter. The literal meaning of filter is that it takes something dirty and produces something clean. So at step k plus 1, you have a state. Your system has reached step k plus 1. You have a state, and you're trying to figure out what is the best, cleanest estimate of the state at step k plus 1. So in this lecture, we'll try to find that. So we start with an example, a very simple example. We again take a simple integrator, which is driven by this input. We collect this measurement y. The state dynamics is also driven by this noise wk, and our measurement has this error vk. So like I said, a filter uses the output at step k plus 1 to estimate the state at step k plus 1. So like we did in the case of a predictor, we will start with the copy of the dynamics. So x hat k plus uk, this is exactly the copy of the original dynamics. We don't know the process noise wk, so that doesn't appear here. And we have an output error, and we have a gain k that we'll try to optimize. So this measurement y is collected at step k plus 1. So we are looking at the measurement at step k plus 1, and we have to now define the output error. Now, what is the output error? So this is yk plus 1. These are the real measurements, And then you also have your computed. I'm sorry, let me erase this. You are actually estimating x hat k and x hat k plus 1 at these steps. So how? So if we are using yk plus 1 in the output error, what should go here? Well, I've clearly written y hat k plus 1, but I haven't defined what y hat k plus 1 is. Since we don't know x hat k plus 1, how can we write y hat k plus 1? So what we are going to do is we are going to take the best possible y hat k plus 1 that we can use. And the best possible y hat k plus 1 is going to be, yk is xk. So the best possible y hat k plus 1 is going to be just the best we can do just before the step. And just before the step, what we can do is use the original dynamics to see that x hat, all right, oh, let me not write here. This is, I'm trying to save the space. So let me write here. X hat k plus 1 just before the filtering, just before. The best we can do is just use the system dynamics, which is x hat k plus uk. So that's what we'll use for y hat k plus 1. Okay, so now that we have, now that we know what we are going to keep here, I'm just going to write it down here again, x hat k, plus uk. Okay, now that we have this term y hat k plus 1, actually I was supposed to write it here. So I'm just going to write it here also, x hat k plus 1, nope, x hat k plus uk. And now this this measured output yk plus 1 using this equation is xk plus 1 plus vk plus 1. Now we know what xk plus 1 is. Xk plus 1 is actually given by this equation. So I'm going to write that part also, xk plus uk plus wk. Okay, so what I want to do is follow the same steps that we did for the optimal state predictor in the last lecture. So we start by defining the error, and I'm going to define the error as x hat k minus xk. And then we are going to look at the error dynamics. So ek plus 1 is just going to be x hat k plus 1 minus xk plus 1. Okay, what is x hat k plus 1? It's just given by this equation. So I'm going to write x hat k plus uk plus k and k times the output error. Now, this guy is going to be, xk plus, xk plus uk plus wk plus vk plus 1 minus, what am I supposed to write here? Yeah, x hat k minus uk. Okay, and then I have to carry the second term. Xk plus 1 is given by this expression here, the first equation right on the top. So that's going to be xk minus uk minus wk. Okay, now we cancel a bunch of things. We can cancel this and this. We can cancel this guy and this guy. Okay, so that leaves us x hat k minus xk, which is just ek. Okay, so we got this guy and this guy. Then we have this guy and this guy right here. So that's going to be plus k times ek again. Okay, and then we have plus k times wk plus k times vk plus 1. All right. Whoops, I was supposed to get a plus 1 here. Okay, so let me just write vk plus 1. Okay, so, and we can collect these terms. I'm going to get, hold on. So this was xk minus x hat k. So I'm going to get a minus here. So 1 minus k ek plus k Oops, I'm missing a W. Oh, there it is. So we have a minus WK. Oops, so many mistakes. So this, and then, okay, so I was supposed to get the black expression, but I realized that I made a mistake here. But anyways, the error dynamics is given by this equation. Now, this is slightly different from the predictor. If you remember, the predictor actually did not weigh one of these terms. I don't remember which one, but we'll see. Okay, so we had this system, we created a filter. The filter equation looks like this, and I pulled up the equations for the predictor from the last lecture. The predictor actually looks like this. So you can see that the error term is the same. The process noise term is also exactly, well, it's not exactly the same because actually the filter has a +1 here that I'm missing. And the W term, which is the measurement, the process noise. I'm sorry, VK was the measurement noise and WK was the process noise. WK actually gets this gain, which was not there in the predictor. So of course, by choosing K, now we are affecting all three of these terms in the filter, as opposed to just two terms as we saw in the predictor. So now we are going to run the same experiments we did last time. I'm going to have x naught equals 1 in my true system. My estimator state is going to start from a 0, which means the error is going to be 1. Again, it's going to be -1. I made so many mistakes. The process noise and the measurement noise are going to be assumed to be Gaussian 0 mean with the variance of 1. And I'm going to propagate this, both these systems for 100 steps, and then I'm going to compute this error metric for a constant value of K, and then I'm going to plot these numbers, and then we'll see what happens. So let's say K was equal to 0. If K is equal to 0, the filter and predictor end up being the same thing. Intuitively, basically, we're not injecting anything, so it's just the original dynamics. So if that's the case, the error sort of diverges, and the cost, this error metric cost, is this number, 68. Okay, we got to keep track of this. Now, when I set K equals 0.5, this cost immediately comes down. And we see that the error is also much lower than it was in the previous case. But the thing to note is that when a filter is used, the cost is actually even lower than the predictor. And you can see that the red trace is slightly smaller than the blue trace. So I'm using exactly the same samples of the noise to propagate both the filter and the predictor state estimates. And clearly the filter state estimates are slightly better. Again, in all these experiments, I made a stupid mistake. This should be VK plus 1. Okay, and if I increase the gain even higher, the performance of the predictor and filter both gets worse. But still, the filter is better performing than the predictor. So now, of course, we can do these types of experiments to figure out what the gain K should be. So we have to have a more systematic method of estimating or computing the gain K for the filter. So we're going to start with the same assumptions that we did. For the case of the predictor, we have our system, and the system gets the input U and produces an output Y, which we measure. We assume that we know what these ABCD matrices are. We assume that the input U is known. We assume that the process noise W is a Gaussian 0 mean with variance 1. We assume that the expected value of the initial state. So first of all, we assume that the state X, well, we don't assume because W is a random variable. We see that the states are random variables. So we assume that the expected value of the state at the beginning of the process is X bar. And we also assume that the initial state and the process noise are independent, which means that the covariance of these guys is going to be 0. Okay, so like last time, again, we observed that since wk is a random variable, the state and the outputs are also random variables. And since wk does not affect the state at the step k, it only affects the state at step k plus 1, the covariance of the state and the process noise is also going to be 0. All these assumptions are used to make some simplifying steps, to justify simplifying steps in the derivation of the Kalman filter or the optimal filter. So here is how we construct the two-step filter. So you have the equations, the system equations, and I write the output equation slightly differently since we are using yk plus 1. So I write yk plus 1 equals the state at k plus 1 and the noise at k plus 1. So we are going to break the estimator now in two parts. The first part of the estimator is going to be the dynamics. So it's just going to use the dynamics of the system to push the state forward. So I can try to make a picture and hope to explain it a little bit better. So we are at step k, and we want to go to step k plus 1. So we know that we have an estimate of the state at this point. It's called x hat kk, and I'll tell you what x hat kk means. So we use the dynamics of the system, which is given by AB matrices, to produce this x hat k plus 1 given k state estimate. So the state estimate at step k plus 1 by the first step of the estimator is denoted by this variable. Now this we call the prior estimate of x k plus 1. And prior to what? It is prior to the actual filtering step. So once we have this prior estimate, we put it, this is the prior estimate. We add this correction term, which is the scaled output error, and we call whatever we get once we have the filtering step, we get what we call as the posterior estimate. So that's after the filtering. That's why it's posterior. So the first step is taking advantage of the dynamics of the system, and the second step is using the measurements to improve the prior estimate. So this stage is prior, and this guy is posterior. And these are standard terms used in the Kalman filter literature. And like we did the last time, we're just going to optimize this gain k. And let's see how we do that. So we have to define a bunch of errors and covariances like we did last time. So this is our real system, and this is our estimator, which is broken down in two parts. This is the dynamics, and this is the filter part. Filter. And what we're going to do is we are going to define a prior error. Now, a prior error is going to be the state estimate error between, or the error, the difference between the state estimate at step k plus 1 and the true state at step k plus 1. Now, this is going to be the prior estimate, not the posterior estimate. So the prior error is the difference between the prior state and the real state, or the true state. Similarly, the posterior error is going to be the difference between the posterior state and the true state. Now, using these two error variables, we are going to define the prior error covariance and the posterior error covariance. The prior error covariance is just the covariance of the prior state error, and the posterior error covariance is the covariance of the posterior state error. And we are going to choose the gain k that minimizes the covariance of the posterior error. Actually, it minimizes the trace of the posterior. It minimizes the trace of the covariance of the posterior error. And let's see how we do that. So we have to again write down the error dynamics. We have the system, we have the estimator equation. The error dynamics of the prior state is x hat k plus 1 given k minus x k plus 1. There's no hat here, so let me erase that. Okay, so this guy is going to be given by the difference of these two equations. Let me call it 1a and 1b. Okay, so x, I'm going to write a x hat kk plus buk minus a xk minus buk minus d1 wk. Okay, so the inputs get canceled like every time, and we are left with aekk and the process noise term d1wk. Now note that this error dynamics, actually we shouldn't call it dynamics because this is not relating ek minus 1 with ek plus 1k. It's actually relating ek plus 1 given k is dependent on ekk. Now these two are different variables. How should I explain this? I mean, you know what I mean. Okay, so once we have this equation, we are going to write the error dynamics of the posterior error. So this was the dynamics of the prior error. Again, I shouldn't be calling it dynamics, but let's just say that the prior error satisfies this equation and the posterior error is going to satisfy this equation. Okay, so which equation is that? So that's going to be k plus 1 given k plus 1 minus xk plus 1. This is just by definition. And x hat k plus 1 given k plus 1 is given by x hat k plus 1 k plus k times. Now why k plus 1? I'm going to use, so I'm going to call this 2a, 2b. Okay, so I'm going to say from 2b, I have cxk plus 1 plus d2wk plus 1. And then I'm going to subtract of c x hat k plus 1 given k. Okay. Oh my God, so many things. Okay, so this term and this term are exactly the same. So we are going to just collect them. So that's going to be I minus kc x hat. Oh, hold on. I made a mistake. I missed this guy. K plus 1. Yes. Okay. So x hat k plus 1. Oh, maybe I missed a couple of terms. You know what? Let me back up a little and then go at it again. Okay, so I have x hat k plus 1 given k plus 1. I have this. I have k times this guy minus this and minus xk plus 1. Okay, great. So this term and this term gives me ek plus 1 given k. Yep. Yeah, I was going the wrong way. And then we have this kc, and xk plus 1 minus x hat k plus 1 given k is actually minus ek plus 1 given k. And then we are left with the last term, which is k d2 wk plus 1. Okay, so this is better. And then you can collect the terms, and we end up with I minus kc ek plus 1 given k plus k d2 wk plus 1. Oops. Okay, so fortunately, I reached the correct expressions. So the correct expressions, well, the right expressions are given here, formatted much more nicely. So this is the prior error dynamics, and this is the posterior error dynamics. Posterior error dynamics. All right, so what next? Now, using these errors, we have to define the prior and the posterior covariances. So the prior covariance is defined by this expression. Well, it's defined as the covariance of the prior state error, which is defined as the expected value of this giant expression. Now, as before, we would like these guys to be 0 because it makes life so much easier. And I'm just going to argue a bunch of things which allow us to assume that, or not assume, convince ourselves that this term is indeed 0. So, okay, so let's look at the prior state error. So the prior state error satisfies this expression. And if I take the expected value of this expression, I end up with the expected value of the left-hand side. And in the right-hand side, the expected value of W is 0. So I'm going to be just left with this expression. Now, if this term is always 0, then this term is always going to be 0. Okay, that's what this sentence says. Now we move on to the posterior error equation. The posterior error equations, the posterior state error satisfies this equation. And again, I'm going to take the expected value. And when I take the expected value of WK plus 1 is going to be 0, which means that the expected value of the left-hand side is going to be this constant matrix times the expected value of this guy. And again, if I can say that this is 0, then this term on the left-hand side is always going to be 0. So I have to use basically this equation, this sentence, and this sentence to argue via sort of induction that if I start at this condition, if the expected value of E0 given 0 is 0, then all these terms are going to be 0. Now, what exactly is this term? This term is defined as this because the error is defined as this. And we know what the expected value of the initial state is because we assume that it was X bar. So all we have to do is say that the expected value of the initial or the prior state estimate is X bar. If that's the case, we can drop these terms like we did last time. Actually, we can drop both of these terms, which would help us. So this is for the prior state. This is the prior covariance, posterior covariance. Okay, moving on. So we have the prior covariance, and then we have the posterior covariance. Whew. Now the prior covariance, prior error satisfies this equation, which means that the prior covariance is going to be given by this expression. And now again, I was planning to write all these equations. So let me waste some time. And all I'm going to do is I'm going to expand out this expression. So that's going to give me AEK given K given K transpose, A transpose, the D1 WK transpose D1, and then the cross terms. Now the cross terms are going to be 0 because we assume that the errors and the noise terms are not are independent or are not correlated. So since they are independent, the expected value of the cross terms or the covariance of the state error, the posterior state error and the noise is actually going to be 0. So we are going to be left with just these two terms. And since the A's and the D's are constant, I can pull them out. And all I'm going to be left with is this term. And we assume that the variance of the process noise or this noise term W is the identity. So if I take the expected value of this guy, it's going to evaluate to identity. So I'm going to end up with this term. And this term, in the last lecture, I showed you that we just call this Q, which is the covariance of the process noise. This is the model of the covariance of the model. This is the model of the process noise covariance, yes. Similarly, the posterior state error satisfies this equation, and I'm going to follow all the steps again. And we are going to end up with I minus kc and pk plus 1 k I minus kc transpose. And similarly on this side, k d2 times, again, wk plus 1, wk plus 1 transpose. Expected value is going to be the identity. So I'm going to, and we used to call that k. So we are going to end up with this term. Okay, here are the correct expressions. So this is exactly what we got. This is an expanded term of what I got in the previous slide. And I'll, of course, upload these slides to the to Canvas so you can check. So like I said, the optimal gain k is given by minimizing, or is computed by minimizing the trace of the posterior error covariance, where the posterior error covariance is given by this equation. So we see that this is does not depend on k, linear dependence on k, linear dependence on k, quadratic dependence on k. And when we take the trace of these guys, we end up with scalars. Trace, again, is the sum of the diagonal entries. Now, the minimizer, this gain k minimizer, let me back up. So the minimum of the trace pk plus 1, k plus 1, the gain k that gives us the minimum trace pk plus 1, pk plus 1, k plus 1. Oh my God, so many k plus 1s. Okay, again, let me say it again. So the gain kk, which minimizes this guy, the gradient of this guy at that particular kk is going to be 0. So we have to get the derivative of this right-hand side with respect to gain k. And we can use these formulas here to differentiate the trace of a matrix with respect to another matrix. Using this formula, we find that the derivative of trace p k plus 1, k plus 1 is actually equal to this guy. And when we set this equal to 0, when we set this equal to 0, we get the optimizing gain, which is simply obtained by moving one of these guys to the right-hand side and then post-multiplying by the inverse of this. Now, post-multiplication, of course, requires that this matrix be positive definite. Now, we know that the covariance matrices are positive definite. This guy can end up being 0 because C can be 0. So we need R to be positive definite. So the measurement noise must be positive definite for this optimal gain to make sense. And this is the same condition that we had the last time, that the process noise covariance should be positive definite. Okay, so that's all there is to an optimal filter. You have the dynamics step, you have the filtering step, and in the filter, the gain kk is given by this equation, where the prior covariance is updated using the dynamics, and the posterior covariance is updated using this equation. So a Kalman filter is basically these 5 equations. Once you implement these 5 equations, that's all a Kalman filter is. So now let's look at some of the properties of this case. So like we saw in the previous lecture, I'm again going to use the simple example. Actually, I used this example earlier also. We have a simple integrator. We have the input u, the output y, and the state is also driven by this noise w, and the output is corrupted by is also corrupted by the noise. And these wk's are actually the wk is actually a vector in this case, and the choice of d1 and d2 makes sure that the process noise and the measurement noise are independent of each other. Okay, so we start with writing down the estimator equation. The estimator equation consists of first the dynamics and then the filtering step, where gain kk is going to be given by the equations that I showed you on the previous page. And when I set A equals 1, B equals 1, C equals 1, D equals 1, sorry, D1 equals 1, and D2 equals 1, I basically end up with these equations. These are pretty simple equations for a one-dimensional system. Now let's assume that our posterior covariance converges. If that were the case, I can substitute these guys here, and then I'm going to get the dynamics of the posterior covariance. And if that is the case, then I can replace all of them by P infinity infinity, because if PKK converges, then this term, the difference between these terms goes to 0. Anyways, once I set P infinity infinity in these equations and solve for, so we are going to get a quadratic equation. And once we solve for P infinity infinity, we are going to see that we get two solutions. One is going to be negative, one is going to be positive. We throw away the negative because covariances are always supposed to be positive. We keep the positive solution, and that positive solution is actually given by this term. And K infinity, the corresponding optimal gain, is given by this term. And these two figures actually show that if you were to implement these equations with various different values of P naught naught, so yeah, I didn't say that we have. So P naught naught is the, it's like the tuning parameter, or it's like a hyperparameter that you choose. So you can choose a bunch of different values and see how quickly or slowly your state estimates converge. General rule of thumb, larger this P naught naught is, more aggressive your estimator is going to be, more aggressive your filter is going to be, more quickly you're going to converge. But the quicker you are, more transients are possible. Anyways, I haven't shown you those examples, but hopefully in homeworks you'll see that. Okay, so now we asked the same question we asked in the previous lecture. Does the optimal filter improve accuracy? You know, we are going through all these hoops to implement this filter, but is it getting us anything? Is it improving the accuracy of the, you know, our measurements? So to do that, we will consider this example. We are again considering a scalar system where the state propagates by this equation and the output is computed by, is described by this equation. We can write the state as the optimal filter or the Kalman filter for this equation, for this system, simply as this. Actually, I'm missing a bunch of terms here. I must have just copied. So this is missing an A, and this is missing a B, and this is, so since we are measuring the state X, the C matrix is equal to 1 in this case. The covariance is, the variance of the process noise is going to be Q, because I'm going to do this matrix times this matrix transpose. So I'm going to end up with a Q for the variance of the process noise, and I'm going to end up with R for the variance of the measurement noise. So our three equations which are used to compute the gain K, the prior covariance, and the posterior covariance for the special case of C equals 1 and big A and big B being equal to small a and small b, we end up with these equations. Our prior covariance propagates by this equation. Our optimal gain is given by this equation. I'm sorry. And the posterior covariance is updated by this equation. Okay, so recall that in the last lecture, we saw this behavior. If we propagated the covariance into the future, and we collected all the values of converged covariances, we saw that, let's just focus on this side. We saw that if the process noise was less than the measurement noise, then the state estimate covariance or the state error covariance ended up between these two values. And if the other if we had the other case where the process noise, um, this is the process noise, is greater than the measurement noise, then your state estimator actually produces worse state estimates. So in that case, you're better off without using the state estimator and just completely relying on the measurements. So something surprising happens in the case of a filter. Okay, I have to show you a bunch of math before I show you the plots. But anyways, so if we do a little bit of math and we remove the prior covariances and we only look at the posterior covariance dynamics, we end up with this equation. And again, we are going to assume that this guy converges. So if it converges, so this guy, and this guy, they all end up with the same values. I'm going to call it P infinity given infinity. And if I replace this guy back here, I'm going to end up with a quadratic equation. This quadratic equation is going to have two solutions, and we are going to look at both of them. But first, we got to look at a special case, the case where A is 0. If A is 0, I lose this quadratic term. And then in that case, P infinity given infinity is simply given by this expression, which we actually recognize as the harmonic mean. So if we don't have any dynamics, that is the dynamics matrix A is equal to 0, in that case, we are only weighing the state and the noise in the inverse proportion of their variances. So P infinity is going to be given by this expression. And I think there's a property that harmonic mean is less than either Q and R. So it's going to be less than Q and it's going to be less than R. Okay, what about A not equal 0 case? So if A is not equal to 0, then like I said, this is a quadratic equation. It's going to have two solutions. One is going to be negative, one is going to be positive. We throw away the negative and we only look at the positive solution. So the positive solution is actually given by this equation. This is nothing but minus B plus minus. I just use the quadratic formula to write this term. So like I said, we throw away the negative, we just keep the positive one. And then we stare at this equation and we try to draw some conclusions. So we look at some special cases. So let's look at the case where Q is equal to 0. So if Q is equal to 0, then this term goes to 0. This is going to go to 0. And then minus this plus I have exact same term. So this whole thing is going to evaluate to 0. So what this is saying is that if the model is good, your process noise is 0. No matter how bad your sensors are, the estimator actually converges to the true state. So your filter estimates are going to converge to the true state. Now, on the other hand, let's suppose the measurement noise was 0. So if you look at this equation again, you see that if R is 0, the second term goes to 0. And again, I'm going to end up with a 0 for P infinity given infinity, which is saying that if the sensor is perfect, that your measurements have no noise, no matter how bad your model is, the filter state again converges to the true state, which is actually quite surprising. This was not the case for the predictor, but for filter, this is the case. So if both the measurement noise and the process noise are not 0, we know that well, we'll see from simulations, numerical simulations, that the converged state error covariance is smaller than both. And if one of the things was perfect and the other was bad, the use of filter compensates for the bad one, and you still end up with absolutely converging state estimates. Yep, this is the figure that I was talking about. So this is the same figure, same type of experiment that I was doing for the predictor. I'm going to evaluate P infinity for a bunch of different values of R. These R values are shown here in red dashes, so 10 to the minus 6, 10 to the minus 4, 10 to the minus 2, and 10 to the 0. And I'm going to, in each case, I'm going to evaluate P infinity for a bunch of different values of Q and various values of A. And we see that in both cases, Q less than R and So I'm going to write here, Q less than R and Q greater than R. In both cases, the conversed or the asymptotic state covariance, state error covariance is actually less than the measurement noise. So the filter always improves whatever you are getting from your measurement. And like I said, if your model is really good, your state error covariance is going to go down really fast. And this is again the comparison with the last, the predictor experiment. And well, I showed you in pictures, but let me try to convince you a slightly different way that the filter is actually better than a predictor. So here is the covariance update equation for filter, and here is the covariance update equation for a predictor. So of course, these terms are different. So this is the posterior covariance, and there was no posterior or prior. There was just a covariance of the predicted state in case of predictor. So clearly, we can see in the case of A equals 0, as I showed earlier, that the posterior covariance is given by this guy, and the covariance, the state error covariance in case of a predictor is given by this guy. Both of these covariances are evaluated or are valid for the state at step k plus 1. Clearly, this guy is less than k, and this is equal to k. So of course, the filter is actually much better than a predictor. A slightly different way of looking at it is actually this. We have, what was I thinking? Yeah, you look at these two terms, and then you find out, look at the numerator. So we have this term and this term are exactly the same. So we are going to assume that at step k, so this is k plus 1. So let's say this is our pk, and let's say this is also our, the exact same value is pk plus pk given k. And we want to see how they propagate into the future. This might be, I'm sorry. My guess is that this is pk plus 1 and this is pk plus 1, k plus 1. So let's see if we can just look at these equations and convince ourselves that that is the case. So look at this filter. Now, if the posterior covariance and the predictor covariance are exactly the same, this term and this term are going to be same. QR and QR is going to be the same. Now your predictor has this one extra term, so that if you have an extra positive term in the numerator, clearly this guy is hopefully going to be larger. Now let's look at the denominator. So if you look at the denominator, the larger denominator produces a smaller net value. So is this denominator smaller than this denominator? Now looks like if I multiply with a squared, I'm probably going to, and if a is less than 1, then this guy is going to be less than this guy. We have the same r, but the covariance, we have this one extra q term. Well, this makes it larger. Well, q makes it larger, but a square possibly can drive down pkk. Well, if a is greater than 1 and q is greater than 0, the filter denominator is going to be larger than the predictor's denominator, and hence this term is going to be much smaller. So what I'm saying is pk plus 1, k plus 1 is going to be less than pk plus 1, which is actually great. So a filter produces much better estimates than a predictor. And this is also an intuitive result. If we think about it, filter is actually using the information at step k plus 1 to produce an estimate of the state at step k plus 1, whereas predictor is only predicting into the future. It doesn't have all the information. So the more information you have, the better you're going to do in terms of your in terms of the accuracy of the estimates. So the filter is, of course, better than the predictor. Now, for both the predictor and the estimator, sorry, for both the predictor and the filter, I assumed that the system was LTI, which is linear time invariant, and the noise characteristics were constant in time. That is, the D1 and the D2, which allowed us to write Q and R, were constants. But actually, they don't have to be. I only did that because it gets messy carrying around all these indices. You can carry exactly the same sort of derivation, and if you set the matrices, instead of writing ABC, D1, D2, you wrote A sub k, B sub k, and so on, you will find that the equations of the estimate of the predictor and the filter are exactly the same. All you have to do is just replace all the A, B's with A sub k and B sub k. Actually, C sub k is replaced by CK plus 1 because we are looking at the predicted output at step k plus 1. So A is replaced by AK, Q is replaced by QK, C is replaced by CK plus 1, and R is going to be replaced by RK plus 1. So all the equations that we derived are exactly applicable to linear time variant, discrete time, linear time variant systems also. You just need to know what these ABC matrices are going to be. And in fact, in the particular applications in navigation, we are going to see that we are going to be dealing with these LTV systems, and we are going to evaluate these matrices at every time step k and use them in our filters or predictors. So to summarize, in this lecture, we saw how we can use the measurement at step k plus 1 to improve or to construct an estimator which produces an estimate of the state at step k plus 1, and it is called a filter in this case. And in the next lecture, what I'll do is I'll start formulating some navigation problems, or all navigation problems as state estimation problems. And then I'll show you how we can apply this Kalman filter in navigation problems, both inertial and non-inertial. Actually, in the inertial case, Kalman filter, there is a surprise. The Kalman filter actually, you know what? Let's just wait for the next lecture. Anyways, thank you so much again for listening. Have a good day.